Okay, so I wanted to do two more quick examples showing how to use and think about uniform continuity. So just as a reminder, here's our definition. So function f from domain A to R is uniformly continuous on A if for all epsilon there exists a delta, so that if x minus y is less than delta, then f of x minus f of y is less than epsilon. And remember, our important point here is that the same delta works for all points in the domain simultaneously, right? So this quantifier for all is coming after the delta has been picked. Okay, so this is our big point about uniform continuity, that the same delta works simultaneously for all points. Okay, so I claim the following theorem is true. So if f is a uniformly continuous function and g is also a uniformly continuous function, then their sum is still uniformly continuous. And this feels a lot like the algebraic limit theorem type problems that we've seen many, many times before. So let's start by just sketching part of a proof. All right, let's see how to understand this. So I want to show that f plus g is uniformly continuous. That means I need to estimate f plus g of x minus f plus g of y. Okay, so of course I'd like to make this whole thing less than epsilon. Well, let's start by just understanding what is this expression, f plus g of x. Of course it's f of x plus g of x. By definition, this is how we add functions, minus f of y plus g of y. Okay, so after a little rearranging, I see that we'll have f of x minus f of y plus g of x minus g of y. Alright, so at this point it looks very much set up for a triangle inequality, so we'll go ahead and do that. Triangle inequality will give us absolute value f of x minus f of y plus absolute value g of x minus g of y. Okay, so why is this good at this point? I've gone through all this work, and what we see is that we've created terms of the form f of x minus f of y, which I can control, right? If I know that f is uniformly continuous, then I know there is some delta, right? I get some delta, which guarantees that this first expression can be made less than, say, epsilon over 2, right? So there's a delta corresponding to this f, okay? So I definitely need x minus y less than some, I guess it's going to be delta 1, right? Because it corresponds to this f term, okay? And then something similar will happen for the g terms, right? I want to force the g of x minus g of y to be less than epsilon over 2. Of course, all this will work out to be just right. But to make this happen, okay, because g is uniformly continuous, I know that I can get some, given any epsilon over 2, right? There exists some delta 2, so that if x and y are at most delta 2 apart, then this will be true, right? I'll get this to hold. So of course you see, well, I'm going to have to use some sort of minimum of these two delta, okay? But with all this sketched out, it looks like we'll be able to get the problem to work out. Okay, so let's write our formal proof. Let epsilon be bigger than 0. And so now we need to invoke these uniform continuity of f and g in order to create delta 1 and delta 2, right? So let's say by uniform continuity of f, there exists a delta 1 bigger than 0 so that if x minus y is less than delta 1, then f of x minus f of y is less than epsilon over 2. Right? We don't want epsilon here. We need epsilon over 2 because we know the triangle inequality is going to take effect later. Okay. Okay. So of course we'll do the same thing with g. So by uniform continuity of g, Similarly, we say that there exists a delta 2 bigger than 0, so that if x minus y is now less than delta 2, then g of x minus g of y will be forced to be less than epsilon over 2 in absolute value. Okay. So, in order for both of these to be true, right, I want both the f inequality and the g inequality to both hold. So, of course, we'll take, as we've done many times before, delta to be the min of these two values, delta 1, delta 2. Okay. By taking the minimum, I guarantee both of these inequalities will hold, and so both f and g inequalities will also hold. Okay, so now, if x minus y are any two numbers less than delta, then now our scratch work takes over. F plus g of x minus f plus g of y equals f of x plus g of x minus f of y plus g of y, which equals, after a little rearranging, again, this is all repetition of what we did before, f of x plus, minus f of y plus g of x minus g of y. And using a triangle inequality, this is less than or equal to f of x minus f of y plus absolute value g of x minus g of y. But now, of course, because we've chosen our delta super duper small, each of these is less than epsilon over 2, which gives us an epsilon at the end of the day. Okay, QED. Okay, so this proof works sort of how we hope it would work. You know, if I didn't tell you that this was a uniform continuity proof, it would sort of look like a lot of ingredients we've seen before, right? Triangle inequalities and taking delta to be the minimum of two other choices of delta. So in some sense, a lot of the techniques we've learned before will roll over into this section. Okay, so a natural question which follows this is, what happens if I consider the product of two uniformly continuous functions? Well, I claim that this one doesn't work as well. So if you want, you might want to pause the video to think about what might happen if I multiply two uniformly continuous functions. So you can come up with a counterexample here. And indeed, you might come up with the following two examples. So take f of x and g of x, each to be x. I'm going to take these on our domain real numbers. Okay. So I claim that both f and g are uniformly continuous. Well, of course, they're the same, so if one is, then both will be. And the problem is going to be this: f times g of x equals x squared. Okay. So I claim that x squared is not uniformly continuous. How can we check? Well, if we take our sequence criterion for non-uniform continuity, we might want to consider sequences xn, which are the sequence n, and yn, which is the sequence of n plus 1 over n. Okay. So this is the exact same sequences that I took for the x cubed example we did in class, right? So you can check, okay, so maybe you should check that the absolute value of xn minus yn does indeed go to 0, but I claim that this square is going to mess us up, okay? So absolute value of f of xn minus f of yn equals, so what do we get? I plug in the n to get n squared, minus, plug in the y's, I get n plus 1 over n squared. Okay, what's this equal to? Well, okay, I'm going to skip a little bit of the arithmetic here. You'll trust that hopefully I did this right. So I get n squared minus n squared, so I'm going to get 2 and plus 1 over n squared, which of course is bigger than or equal to 2, and this is true for all n in the naturals. Okay, so you see that we get some epsilon naught, in this case equal to 2, so that the distance between my y values when I plug in my sequences are always bounded below, the distance between them is bounded below by 2. Okay, so this shows that this is not uniformly continuous. Okay, so even though, and we proved in class that other linear functions, so you can quickly check, or you can hopefully understand quickly why linear functions are going to be uniformly continuous. The product of two linear functions, which might be x squared, is not uniformly continuous. So in general, we can't say anything about products of uniformly continuous functions. Okay, hopefully you find these examples helpful. If there's any questions, please let me know. We'll talk about it in class or in office hours. All right, have a good weekend.